Okay, so good morning everyone. Today's session is going to be in English. But before we start with the actual session, I see that there are several English-speaking people in the audience as well. I'm going to start with an intro in Hebrew. This is the Israeli Data Platform Meetup. So I'm going to switch to Hebrew now, and then we'll go back to the actual session itself with Hugo in English. אז בוקר טוב לכולם, אנחנו מפגש נוסף של Data Platform Meetup. היום יש לנו אורח כבוד, יוגו קורנליס, תכף אנחנו נציג אותו, ולכן גם הסשן יהיה באנגלית. אבל לפני זה, כרגיל, קצת חדשות ועדכונים ומה שקורה בעברית, מה קורה בקהילה שלנו. אז אני אתחיל ככה עם המצגת. קודם כל, למי שעדיין, אם יש כאלה שלא מכירים, שחדשים פה וכולי, אז זה הלינק למיטאפ שלנו, הישראלי, דאטה פלטפורם מיטאפ, כל האירועים, כל מה שאנחנו עושים מפורסם שם, באתר. מי שעדיין לא רשום, מוזמן להירשם, ואז תקבלו עדכונים על מפגשים חדשים שלנו וכל מה שאנחנו עושים. קבוצה בפייסבוק, יש לנו קבוצה מאוד פעילה, יש שם, לא זוכר בדיוק כמה, בסדר גודל של 2,000, אם אני זוכר נכון, חברים, דיונים מקצועיים, מחפשי עבודה, מחפשי עובדים, whatever, כל דבר שקשור לקהילה, בגבול הטעם הטוב כמובן, במטרה לעזור אחד לשני, קורה שם, מוזמנים גם להצטרף, לקחת חלק בדיונים, אז זה בפייסבוק. במקביל אלינו יש את ה-Global Hebrew Virtual Group של פס, שמוביל רונן אריאלי, אוסף של גם כן וובינרים בעצם, היום זה הכל אונליין, כן, אז זה כבר לא משנה, כל פעם בנושא אחר, הפואנטה שם שזה תמיד בעברית, אז למשל שם לא יהיו מרצים באנגלית, שם זה רק עברית, מצד שני שם יכולים להיות מרצים מכל העולם, אז זה גם קורה במקביל אלינו, גם שם יש וובינר לא מעט, איפה נדבר על אחד מהמפגשים שקורים ממש בקרוב, שרונן עצמו הולך להעביר. ערוץ היוטיוב שלנו, לשם אנחנו מעלים את כל ההקלטות, כל הסשנים, כולל מה שנעשה היום, גם כן יהיה מוקלט ויעלה לשם, מוזמנים להיכנס, לראות את כל הסשנים שהיו עד היום, לעשות סאבסקרייב לצ'אנל הזה כדי לקבל עדכונים על דברים שאנחנו מעלים לשם וכולי. ודבר אחרון, SQL Server Radio, איתן ואני מבלבלים את המוח על SQL Server, מוציאים תוכנית פודקאסט פעם בחודש, יש גרסה גם בעברית וגם באנגלית, זה הלינק לגרסה בעברית, אז אם אתם עדיין לא שם ואתם מתעניינים ב-SQL Server, ואם אתם פה אז אני מניח שאתם מתעניינים, מוזמנים לעשות סאבסקרייב, ופעם בחודש להאזין לפודקאסט שלנו, זה משהו כמו חצי שעה, 40 דקות, כל תוכנית כזאת, עם הרבה דברים מעניינים שקורים. אנחנו חלק מפס, ארגון העולמי שמאגד בתוכו את כל משתמשי המייקרוסופט דאטה פלטפורם בעולם, ארגון ללא כוונות רווח, שעושה הרבה מאוד דברים, חלקם בחינם, חלקם בתשלום. אתם מוזמנים להירשם, הרישום עצמו בחינם, ואתם כבר זכאים ללא מעט דברים. מי שעדיין לא רשום כממבר בפס, אז תיכנסו לאתר שמופיע פה ותירשמו. יש הרבה מאוד דברים שפס עושים, בין היתר תיכנסו באתר ותראו שם לא מעט ריסורסים, הקלטות של סשנים, אירועים שהיו בעבר, יש שם המון, תוכלו לעשות סאבסקרייב לכל ה-Virtual Groups, כמו ה-Global Hebrew שהזכרתי קודם, יש הרבה מאוד Virtual Groups, הכל נמצא באתר, תכף אני גם קצת אזכיר את זה. האירוע הכי גדול, הכי משמעותי שפס עושים, פעם בשנה, זה פס סאמיט, בדרך כלל זה קורה, זה אירוע פיזי כמובן בארצות הברית, השנה כמו כל דבר אחר זה וירטואלי. אם אפשר רק תעשו מיוט, יש פה איזשהו רעש, אני אראה מי עושה לנו רעש. רגע, אני אעשה קצת עול. אוקיי, סבבה. אז פס סאמיט השנה הוא וירטואלי כמובן, וזה קורה בנובמבר. זה שהוא וירטואלי, זה בעצם הזדמנות מעולה בשבילנו הישראלים, כי בדרך כלל לנסוע לכנס הזה זה עולה הרבה מאוד כסף. זה גם הכרטיס עצמו מאוד יקר, וגם הטיסות והמלון, וכל הלוגיסטיקה מסביב. זה גם החוויה כמובן שאנחנו מאבדים פה, אבל מצד שני יש פה הזדמנות להצטרף לכנס הזה, שהוא באמת גדול, מרשים, כל המרצים הטובים בעולם, המון מסלולים במקביל, המון תוכן, אז גם הכרטיס השנה הרבה יותר זול, כי זה וירטואלי, וגם אין את כל הלוגיסטיקה, זה הכל מהבית, אז זה מאוד נוח, אז יש פה הזדמנות באמת גדולה, ממליץ להירשם לכנס הזה, תיכנסו לאתר, תסתכלו על כל הסשנים כבר הוכרזו, יש גם סשנים, גם pre-con sessions, שזה סמינרים של יום שלם, גם יוגו לדעתי יש לו, יוגו, you have a pre-con session in PAS Summit, right? You're
Sorry,
muted.
I had to unmute. Yeah, yes, I have a pre-con at the PAS Summit, correct.
Excellent. So,
and I'm also doing I think 2 breakout sessions.
Cool, great. אז ליוגו כמובן יש כמו שאמרנו, סמינר של יום שלם, זה בתשלום נוסף, אבל תבדקו, execution plans, בזמן כדאי להירשם לזה. ויש לו גם סשנים באירוע עצמו, לי יש גם כן, אני מאוד גאה שקיבלו אותי להעביר הרצאה גם כן בסשן עצמו, באירוע עצמו, יש שם הרבה, תיכנסו, תסתכלו, ואם אתם נרשמים, איפה זה? אז הנה זה פה, אז יש את הקוד הזה, קוד הנחה, מה שמופיע פה למטה, תרשמו אותו, זה מקנה לכם $50 הנחה בזמן הרישום, אז עוד יותר סיבה טובה להירשם, בכלל יחסית לשנים קודמות, אז המחיר באמת באמת אטרקטיבי הפעם, תבדקו, כנסו לאתר של פאס סאמיט, ותראו כל מה שמחכה לכם שם. חלק ממה שיש בפאס סאמיט, אחד מהדברים שאני מאוד אוהב באופן אישי, זה ספיקר איידול. כל שנה עושים את זה, זה בעצם נותנים הזדמנות לאנשים בלי ניסיון, בלעמוד על במה מול קהל ולהעביר הרצאות וכולי, נותנים צ'אנס לאנשים, יש מין תחרות, זה קצת כמו ריאליטי כזה, מין כוכב נולד כזה, לכל אחד אם אני זוכר נכון יש 7 דקות או 10 דקות, משהו כזה, להעביר איזשהו נושא, ועושים ככה תחרות בין כולם, זה נורא נחמד, זה נורא יפה, חלק מההרצאות הכי טובות שראיתי, באמת, היו דווקא שם, בספיקר איידול, על ידי אנשים שלפני כמה שנים ראיתי אותם, והם היו אז, אף אחד לא הכיר אותם, והיום הם מרצים נחשבים ומוכרים, וזה בעצם פתח להם דלת. אז אם יש מישהו שרוצה, זה גם יהיה מן הסתם אונליין השנה, אז תיכנסו פה ללינק שמופיע למטה, תירשמו, תציעו את עצמכם, תציעו איזשהו אבסטרקט, מומלץ, הזדמנות מעולה. הזכרתי את ה-Virtual Groups, אז יש במסגרת פאס, יש הרבה מאוד Virtual Groups לפי נושאים, יש כל מיני נושאים מקצועיים, אפשר לראות פה DBA Fundamentals, Hybrid, והנה ה-Global Hebrew שהזכרנו קודם, יש פה הרבה מאוד אירועים, פשוט תיכנסו לאתר של פאס, תעשו סאבסקרייב ל-Virtual Groups שמעניינים אתכם, ותקבלו עדכונים על כל מה שקורה, יש פה דוגמאות לכל האירועים הקרובים שקורים באוגוסט ובספטמבר, לא יעבור על זה כרגע, אני אחר כך גם אפיץ את המצגת הזאת כמובן, יש הרבה, כמו שאתם רואים, הרבה מאוד, הכל בחינם, הכל זמין לכם, בכל אחד מה-Virtual Groups יש להם גם אתר עם Meeting Archive, אז אפשר להיכנס ולראות את כל הוובינרס שהיו בהיסטוריה של אותו Virtual Group, ולצפות בכל הקלטות של הכל, המון 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 חומר מעולה, בחינם. תשתמשו בזה. גם SQL Saturdays, שבדרך כלל זה אירוע של יום אחד, שמארגנים אותו בכל מיני מקומות בעולם, גם בישראל אנחנו עושים את זה פעם בשנה, אז גם זה, יש לא מעט SQL Saturdays השנה שהפכו להיות Virtual, אתם רואים פה את הרשימה, וזה גם משהו נחמד, כאילו, במצב רגיל, לא הייתי נוסע עד ללימה, בשביל להיות חלק או לדבר אפילו ב-SQL Saturday, בכל זאת, אין הצדקה לדבר הזה, זה המון עלויות וכולי, אבל השנה, וואלה, זה וירטואל, אז אני יכול להשתתף גם ב-SQL Saturday לימה, וגם באוסלו וגם בסולט לייק סיטי וגם בהרבה מאוד מקומות אחרים, כי זה הכל וירטואל. יש פה הזדמנות להיכנס ולראות איזה אירועים יש בעולם, ופשוט לעשות רג'יסטר ולהצטרף אליהם, ולהיות נוכחים ולהשתתף בהרצאות שיש שם, או להציע את עצמכם כספיקרס, גם זה רלוונטי, אז גם תבדקו. אני לא אתן עכשיו זמן לאנשים את זה, כי בדרך כלל זה לא קורה גם ככה, אבל אני כן חוזר ואומר, חלק ממה שהקהילה הזאת, התפקיד שלה זה לעזור לאנשים, לעזור אחד לשני, ובתקופה הזאת יש לא מעט אנשים שאיבדו מקום עבודה, שיצאו לחל"ת, שמחפשים עבודה, זה המקום שלנו לעזור ולחבר. יש פה הרבה מאוד אנשים בקהילה הזאת, אנשים שמחפשים עבודה מצד אחד, ואנשים שמחפשים עובדים, שמייצגים חברות שחפשות עובדים מצד שני, המקום שלנו זה לחבר ולעזור במקומות האלה. אז אם לא נעשה את זה כאן, לפחות נעשה את זה או בפייסבוק, שזה יש את הקבוצה בין היתר, תפרסמו שם את המשרות שאתם מחפשים, או את עצמכם אם אתם מחפשים עבודה, או פשוט תפנו אליי באופן אישי, אני אשמח מאוד לעזור ולחבר, אני מכיר גם כאלה וגם כאלה, ואני יכול לעזור לחבר, אז דברו איתי אם יש פה כאלה, חשוב שנעשה את הדברים האלה גם כן. קצת על אירועים, לפני שאני מעביר את הבמה ליוגו, אז האירוע הקודם שהיה לנו, לפני שבוע, יוסי אלקיים, למי שהיה, העביר הרצאה ל-Azure Synapse Analytics, הייתה הרצאה טובה, נתן לנו קצת רקע על כל המוצר הזה, ההיסטוריה שלו ואיך הוא נראה היום ומה אפשר לעשות איתו. יש את ההקלטה ואת כל החומרים, את המצגת למעשה של יוסי, בדף של המיטאפ, מה שמופיע פה, מי שלא הספיק להגיע, לא הצליח להגיע, אז מוזמן להיכנס ולראות את ההקלטה של האירוע הזה. זה היה פעם שעברה, בואו נדבר על מה מחכה לנו בהמשך. אז קודם כל, החל מהיום, במשך 4 ימים, יש Azure SQL Bootcamp, מחנה קיץ, אפשר לקרוא לזה, של בוב וורד ואנה הופמן, על Azure SQL Database, כל מה שרציתם לדעת על Azure SQL Database, מומלץ מאוד, זה קורה נדמה לי בין 7 הנה כתוב פה ב7, בין 7 ל9 בערב, כל יום במשך 4 ימים. אז אפשר עדיין להיכנס ללינק שמופיע פה ולהירשם ולהצטרף להיות חלק מזה, יש שם גם הרצאות שלהם וגם hands-on labs כאלה, אפשר לתרגל תוך כדי ולהכיר טוב את הפלטפורמה הזאת, Azure SQL Database, מומלץ, זה דבר אחד. דיברנו קודם על הגלובל היברו, אז ב-23/8, שזה יום ראשון הקרוב, אני לא טועה, כן, יום ראשון הקרוב, רונן אריאלי מעביר הרצאה על Unstructured Data בתוך SQL Server, איזשהו דיון מעניין על האם SQL Server הוא באמת דאטאבייס רלציוני, או לא רלציוני, או לא רק רלציוני, אפשר להשתמש בו גם ב-JSON ו-XML ו-Graph Database ועוד כל מיני דברים. אפשר לעשות הרבה דברים מעניינים, אז דיון מעניין והרצאה שהיא קצת יותר אינטרנל של רונן אריאלי, מומלץ, זה ב-23/8. במיטאפ שלנו, מה מחכה לנו? אז בשבוע הבא יהיה את החלק השני של ההרצאה של יוגו, שתכף אני אציג אותה. יוגו ידבר על hash match operator, וזה בעצם הרצאה מאוד ארוכה, 2.5 שעות, אז חילקנו לשניים, כי 2.5 רצוף זה קשה, אז היום אנחנו עושים 1.25 שעות, ובשבוע הבא, ביום שני הבא, את החלק השני, שזה עוד 1.25 שעות, וב-27/8, שזה יום חמישי הבא, יש לנו הרצאה מאוד מעניינת של עמי לוין, על Database Design, הייתה אמורה לקרות לפני כמה זמן, והיה על הבלטם של רגע האחרון, אז דחינו את זה, אז זה יקרה ב-27/8 בשעה 7 בערב, מומלץ מאוד, מי שמכיר את עמי לוין, אז גם כבן אדם, אחלה מרצה, וגם הנושא מאוד מאוד מעניין, אז מומלץ להירשם לזה. יום שישי, יום אחרי, בשבוע הבא, ביום שישי, ב-28 לאוגוסט, מי שמכיר, יש SQL Friday. SQL Friday קורה בעצם כל יום שישי בשעות הצהריים, המטרה היא ככה סביב ארוחת צהריים לעשות הרצאה על SQL Server או על הדאטה פלטפורם, אז הכבוד שלי להעביר בשבוע הבא הרצאה על סטטיסטיקס ב-SQL Server, הרצאה שהעברתי באיזשהו פורום לא מזמן, אני אעביר אותה באנגלית מן הסתם בשבוע הבא, אז מוזמנים להצטרף להרצאה שלי, ומוזמנים באופן כללי להסתכל באתר של SQL Friday, ולראות שם את כל ההרצאות הקרובות שצפויות. יש כל שבוע ביום שישי איזושהי הרצאה, עוד אחד מהמיזמים היפים האלה שבעצם בהתנדבות, בחינם למען הקהילה, מוזמנים להצטרף גם לזה. והגיע הזמן להציג את יוגו קורנליס, להרצאה של היום על ה-hash match operator. יוגו הוא דאטה פלטפורם MVP, ותיק, תותח על, מומחה לכל מה שקשור ל-execution plans, יש לו הרבה מאוד הרצאות, הוא מדבר הרבה וכותב הרבה על execution plans באופן כללי ועל performance ב-SQL Server. אני באופן אישי מאוד אוהב להיות בהרצאות שלו ולשמוע אותו מדבר, יצא לי כבר כמה פעמים, בין היתר יצא לי לשמוע את ההרצאה הזאת, ואז ביקשתי ממנו לבוא ולהעביר אותה גם אצלנו במיטאפ, ולשמחתנו הוא הסכים. אז אני אעבור לאנגלית. Hugo, this is when I present you, so I told about you a little bit, but I will let you present yourself, of course.
I hope it was sufficiently insulting.
Yes, of course, absolutely.
Everything Guy just said about me applies to him as well.
Exactly, yes. I love that. So this will be recorded. If you have any questions during the session, feel free to raise your hand or to write it in the chat, and I will stop Hugo at some point. Is it okay? And I'll ask you the question from the audience.
Yes, sure. And at what point do I need to stop?
Sorry?
At what time do I need to stop?
We have 75 minutes, so
75 minutes
until 12:30.
Okay.
Israel time. I'm not sure what's your time.
11:30 my time. Okay, thanks.
Okay, excellent. So you can share a screen now and...
Yes. My screen should be there now.
Excellent.
Okay, well, you gave me a great introduction. That was not needed because this session has its own introduction. So I'll shut up now and let the introduction play.
This is an execution plan. If you have never seen one of these, you're probably in the wrong session. Every operator in the execution plan has its own task. Some physical operators can only do one single task, while others support several variations called logical operations. The most versatile of all operators support no less than 11 to 13 logical operations. Some of them change behavior so much that many people think it's two different physical operators. Introducing Hash Match, the operator. In this session, you will learn about all its logical operations. We will dive deep into the internals of this operator, and we will explore its documented and undocumented features. This is going to be a wild ride. If you think it's too much for you to handle, leave now. We will not mock you. At least not when you can still hear it. For your safety, keep your hands, arms, and legs inside the conference room at all times, and please remain seated until the presenter has come to a full stop. Here's your host for today, Hugo Cornelis!
Okay, that's enough. That's enough. You can stop now. Thanks. Thanks. Just for the record, I do not do this for all my presentations. This idea was born when I was on a long ride. I wasn't riding myself. I was in the back of the car. There were two people in front. I was alone in the back. The car was noisy, so I couldn't talk to anyone. The landscape was boring. It was hours and hours and hours. And my phone was almost out of juice, so I couldn't play any games. In other words, I had nothing to do except thinking. You should not give me that much time to think. This is what happens when you give me that much time to think. And the problem with this kind of introduction is it can only go downhill from here. I've set the bar too high. Anyway, I do want to thank my amazing son, Timon, who composed the music based on a generic idea I gave him, and who managed to record the entire text I gave him without laughing out loud. Or he cut it out of the recording, I don't know. Anyway, let's get serious.
Hugo, I have 2 comments. One, if you can just minimize my image there, so it doesn't. Okay, excellent. And second, when you said if you're not ready for it, leave now, someone actually left.
Okay, well, that's taken care of. That's one less negative comment on the end.
Yeah, exactly.
Or the comment is, I didn't feel welcome anymore. Anyway, let's talk about hash match the operator. This is the agenda for 2 sessions in total. So today we will talk about the theoretical foundations, and we will talk about all the logical operations that hash match does. I would say that today is actually only level 400 and not really level 500, but we'll make up for that next week when we dive into level 600 when we go into the memory usage. So on average, the 2 sessions combined should be level 500. So yeah, we're going to start talking about the theoretical foundation. Hash match, the name hash is in there. So what is hashing? What is a hash function? And what is a hash table? And to really understand what hashing is, it's a bit like sorting the laundry. You see, my wife and I have this agreement where we share the household tasks, and things have changed. But a few years back, the arrangement was that she made sure that everything was washed, and then I would fold the laundry, iron it, and put it back in the closets. And there was one part of that task that I really hated. This part, the socks. And because I hated it, I delayed it and postponed it, and the end result was a huge heap of socks, and pairing those is absolute disaster. But I did find that just picking one sock out of this heap and trying to find its counterpart was very ineffective. And I found a slightly less ineffective way, which is to pre-sort it by color. So I first made heaps of the blues, the blacks, the pinks, the Disney prints, etc., etc. And then within each heap, I would try to find the pairs, and that saved me a lot of time. And this is actually a good example of hashing. I was using a form of hashing to save time in sorting the socks. So wrapping this back to computing, a hash function is a function that takes any type of input. It can be a varchar, it can be a datetime, it can be binary, it can be a sock, everything. And then it produces an integer result with a known range. So this heap of socks will be numbered. It is deterministic. So if I have 2 blue socks, they should end up on the same stack. It's okay that the light blue and the dark blue socks end up on the same stack. That's called a hash collision. They're not the same sock. They're not a pair. but they end up on the same stack. But I do not want one light blue sock here and the other light blue sock there, because then I won't find the pair. So it has to be deterministic. And like I said, hash collisions can happen when different data ends up having the same hash value. Hash functions is a topic where many people graduated on because there is so much research to do about hash functions. We're not going to talk about hash functions today except this. So bottom line that I want you to take away is a hash function. You can pour any data type in and the result is an integer. Same input results in the same output. Different input might result in the same output or will result in different output. Now that we know what a hash function is, we can start talking about a hash table. Because what a hash table is a table where all the data is stored, but now organized by the hash value. So every row of data we want gets processed by the hash function to result in an integer, and that integer is the bucket where the value is stored. Just like I look at every sock, determine is it the blue one, is it the Disney print, and put it on the right stack. The reason why the term bucket is used, by the way, this is a fun fact, when professors first started explaining the idea of a hash table, and this is back in the 60s, the professor that explained it, he apparently never did the laundry, so he didn't come up with this great idea of using socks. So what he did was put several actual buckets on stage and throw papers in those buckets to visualize how every row is put into its own separate stack. And because he used actual buckets to visualize this, the term bucket is still used in connection with hash tables. So a hash table is a collection of separate sock stacks or buckets or whatever you want to call them, where a part of the data is stored. SQL Server stores the hash table exclusively in memory. There are many different ways to store hash tables. They're not all in memory, but SQL Server has chosen a specific implementation that I'm going to explain in the next slides, and that is completely in memory. So let's look. When SQL Server has to store data in a hash table, the first thing it does is allocate a structure of 7 pointers for each hash value. So it knows the range of the hash function. If it knows, for instance, that the hash function has a range starting at 0 and ending at 999, it knows there will be 1,000 buckets. So it will create 1,000 structures of 7 pointers each. And just for the record, they are not actually white or yellow in memory. That's just a visualization I use. But the 7th pointer in each structure does have a different function. That's why I highlighted it in yellow. Now this structure is in memory, it's in contiguous memory. So I have on the left side added the numbers to show which hash value belongs to which structure. In reality, those aren't stored. SQL Server knows where the top left bucket is, this one. And if it needs to go to hash value 2, it simply adds 2 times 7 times the size of a pointer to the starting point to know, oh, now I need to be here. So this is allocated in memory. And now we can start storing rows, but we can have only a maximum of 6 rows in each structure because the 7th pointer has a different specific function. So when SQL Server reads a row, it is stored somewhere either in the buffer pool or in working memory. And that row itself just remains there. SQL Server reads the row, it computes the hash, and let's say that the hash is 4. Then it will use the first available slot in the structure for 4 to fill it with a pointer to that row. So the row itself is not moved, it is not stored within the actual memory structure of the table, but the memory is now reserved and the pointer ensures that this area of memory here is now logically connected here via the pointer. The next row is read again, the hash value is computed, and this time the hash value is 1. So now a pointer is added in structure 1. And this continues, and if another 4 is found, well, we just use the next available slot, simple as that. And this continues for a while, and eventually we will reach a point where for one of the buckets, 6 rows are stored. So let's say that after storing some rows, we're here, and I have removed the buffer pool memory area now. Every dot is simply a pointer to somewhere in memory. And now we're going to read a row, and that row also needs to go in bucket 4. But all 6 pointers are already used. So what SQL Server does in this case is allocate an additional 7 pointer structure somewhere in memory. This is not contiguous, this is just somewhere in memory. And now that yellow pointer is used to connect this additional structure to the root structure. So on the left, we have a contiguous base. These are the root structures. And this is an overflow structure where 6 more rows can now be stored. And that works like this. So 6 more rows are stored. And this is where it gets interesting. Now, if row number 13 is stored, obviously yet another structure is needed. I would first have expected SQL Server to just put a pointer in here and connect it to there. But that's not how it works. How it actually works is that SQL Server creates a pointer here to there. So now we have 2 pointers to there, but then it changes this pointer to connect to the new structure and uses that to connect to point to the new row. So the effect of this is that we have these first 6 row pointers in the base structure, and then we have 1 or more overflow structures chained together, but the newest overflow structure is always inserted at the start of the chain. And why has Microsoft done this? Well, they haven't documented it, but I think I know why they have done this. Because let's imagine there are thousands of rows in a single bucket. The chain would get very long. So just adding a new row would mean to have to traverse the entire chain following hundreds of pointers, which takes a few nanoseconds every time. A few nanoseconds may not be much, but if you do that thousands of times and then do that millions of times, it adds up. By inserting the overflow row at the start, SQL Server always has to check, oh, the base structure is full. Let's look at the first extension structure. Is it not full? Use it. Is it full? We don't care about the rest. We know that the rest is full. We don't have to read the rest. So it only reads the base and the first overflow structure. And when the first overflow structure is full, then it adds a new overflow structure, and it never has to traverse the entire chain. And that's why this weird ordering is used. Now, I told you this is not documented. So how do I know this? I know this by running code and checking the output. So let's jump into the demo. You should be able to see my Management Studio screen now, right?
Yeah.
Okay. So I have already executed the setup script, which takes half a second to a second on my fast instance. What I did here are some dynamic SQL. I don't like dynamic SQL. The reason I do it here is that I figure out where your master file is, and I use the same directory to allocate the demo files. So this means you never have to change anything, and it will still run on your system. And
just a small comment. I want to say that you can download all the session materials you can see here. I already put a link to Hugo's website in the meetup page.
Yes, thank you. I wanted to say that myself, but I had forgotten about it. So thank you. So I've created 2 tables, one called build input and one called probe input. They are filled, they are defined almost the same and are filled almost the same. So in the build input, I have 500,000 numbers that I generate by creating 10 digits, and then cross-joining that. So this generates 500,000 numbers from 0 to 500,000 minus 1. And then I cross-join that with the letters A, B, D, F, and G. So that's 2.5 million rows. For the probe input, I use the same data, but here the letters are A, C, D, and E, and G. So if I start joining those two tables, sometimes for some letters there will be matches, and for some letters there will not be matches. That's the idea. I also have two small empty tables that I will only use in a single demo, just because I wanted to have several different data types. So integers, small int, tiny int. I'm not going to spend much time on that now. What I want to do here is show how I figured out how that hash table building process is done. So let's first make sure we're in the right database. So what I do is I use a left outer join between the build input and the probe input, and they are both CTEs. So the build input, what I do is you get the first 10,000 rows, ordering by the number first and then the letter, with a where clause as well. So I know when I run this by itself, this will be ordered because the top and the order by forces an ordering. And it will be ordered, as you see here, by number first and within the number by letter. The probe input is in this case empty. Key 1 is never less than 0. So I have a probe input for this demo that is simply empty. You will also see me use a lot of hints in this session. Hints are not something you should use in your real code. The reason I use a lot of hints is because in this session I want to force very specific execution plans to show certain behavior, and those execution plans are often not optimal. I don't want SQL Server to do this the fastest way. I want to do it my way because I want to show you guys something. And this is easier than fighting SQL Server to get just the right data and statistics to get the plan I want. I could probably do that if I invested way more time, but this is an easier way. But it's not something I recommend for production use, just for clarity. So if I look at this query and I'll run it with execution plan plus runtime statistics enabled. And I'll first switch to the execution plan to show what is going on here. So we have a hash match doing a left outer join. The build input, and I'm now going to tell you some things that I will explain in more detail and show in demos later. So this is a chicken egg problem. One demo relies on the other, but the other demo relies on the first again. I have to start somewhere. So I'm starting here, and for now you'll just have to believe that the top input is the build input, which is used to create the hash table in memory. What we do here is an ordered clustered index scan, or seek, I don't recall, seek, but it's ordered. So I know that the data is ordered by, well, the order I showed already when I just ran this. So I know that this is the order in which the data will be added to the hash table. And this is important because I can use this to verify the order in which the rows are eventually in the hash table. What the entire query does is a left join with an empty input. This is an empty input, so the left join will find 0 matching rows, but because it's a left join, everything from the left input also has to be output. And what SQL Server does here is, after trying to find matches by processing the probe input, it will finish its work by just dumping out the hash table in the order in which it happens to be in memory. Which is why I know that when I execute this, what I see now is a reflection of the order in which the data is stored in the hash table, which is what I wanted. Now what I see here, and I'm going to scroll up a bit for my comments, and you see there's 2 blocks of comments because it's different for different versions. The hash functions change. There may also be a reliance on processor architecture, memory, etc. So I'm not even guaranteeing that you will get the exact same results as I get when you run it on your system. But on my system, these are the consistent results. And I happen to know that the value 0 is on its own in a bucket. There's no hash collision here. So these rows are just added in the hash bucket in the order in which they were processed. I also happen to know that the values 23 and 687 share a hash bucket. There's a hash collision here. And when you look at this data, you don't see any difference between this block and this block and this block. So how do I know that these two share a hash bucket and this one doesn't? That's for the next query to show. I will show you that later. For now, just believe it. You will see that if there is 10 rows in a hash bucket, the order is normal. Well, that still satisfies what I showed. The first 6 structure, and then the first overflow structure is used. It shows what I just showed on the slide, but it doesn't disprove many other alternative explanations. So let's move to a value where I know that there are 3 rows in the same bucket. That's rows 16 to 30. Let's scroll this up a bit. And here we see for the first time that the order is a bit weird. So the first 6 rows, it starts at 46 to the start of 215. These are the first 6 rows. The next row after this was 215b. And there we have another block of 6 rows. And then the third block of 6 rows, or rather partial block in this case, is inserted in between. So here we already see this behavior of a base structure for the first 6 rows, an extension for the next 6 rows, and another extension that is inserted in between the base and the first extension. Now for the final example, I need to scroll down a bit further, 906. This is the benefit of using comments. So here we see the same again, but now there are 4 values that happen to have a hash collision. So this is the base structure. The first extension now starts here, because after 364A is of course 364B. Oh, that's the wrong click. Whoa, do as I want, not as I click, please. So here is the next block of 6 rows. And then the third block of 6 rows was inserted here. But when that was full, yet another block was again inserted immediately after the base. So every time we see the same order of the base, and then the last assigned extension, which may not be full, and then the other extensions, which are all full, in the wrong order. Well, wrong in the reverse order in which they were the rows were processed. So this output shows why and explains why I realized how SQL Server builds and fills a hash table. Now, like I said, especially at the start, you just had to believe that this is a single bucket and these two are combined in a single bucket. But how do I know, and how did I figure out that these were all in a single bucket? What I actually did first to figure out which values are in a single bucket is almost the same query, but in this query, the only change is that I changed the input order. And by changing the input order, now the input looks like this, all the A values first, and then all the B values. And within each letter, they are sorted. Which means that now, because the hash table is built by getting the rows in a different order, the query results are different. It is still the same effect of outputting the entire hash table after not finding any rows that match the left join. But now you see that this first bucket is still the same. 5 rows were added, now not immediately after each other, there were many rows in between, but 5 rows were added over time to that bucket and nothing else was added. But here you see that these two actually are hash collision. The only explanation for this order is that those rows are in the same bucket and no other rows are in the same bucket. And this is how I figured out where all the hash collisions were and where I had examples of the same of different values in the same bucket. So this is actually what I ran first with some automatic post-processing to find all the hash collisions, which is also why I know for sure what I said in the comments, that on SQL Server 2017 there are no hash collisions between 5 values. On SQL Server 2016 I had 1. So if you are running this demo on your own machine and you get different results, just start with the second query to find where there are weird orders. So the sheer fact that you have 3 A's in succession here already proves that this is a hash bucket that has 3 different values stored in the same bucket. Questions so far?
Probably
Nothing?
not.
Okay, let's continue then. So we covered hashing, we covered a hash function, we covered a hash table. What I didn't explicitly call out, but I kind of hinted at it by using the socks example, is that the idea of a hash table is that instead of having 100,000 rows that are basically unordered, you have maybe 10,000 buckets that on average have 10 rows each. Within those buckets, the data is still unordered, but finding a match in a 10-row bucket or finding a match in a 100,000 row collection is, of course, a huge difference. And that's why HashMatch uses a hash table and then later benefits from it. So let's go through how HashMatch works. And HashMatch can do a lot of things. It has a lot of different operations, but every time it works, it goes through at most 3 phases. HashMatch always has a build phase, most of the time then has a probe phase, and in some cases has a final phase. The reason I use quotes around final is because that's my own terminology. The build phase and the probe phase are actually documented. Microsoft talks about them. Microsoft doesn't talk about the final phase. I think they consider it part of the probe phase, but I don't like considering it part of the probe phase because it's a very distinct and separate action. So I consider it a separate phase and call it the final phase. Not all phases are always used. So let's start with the build phase. The build phase is the only phase that always runs. What the build phase does is it processes the first input. In the execution plan, you will always find this first input on the top side. The official term is called the build input because it's the input for the build phase. What the build phase does is it builds a hash table in memory. That's why it's called the build phase. In almost all cases, the build phase does not produce any output. So while the build phase is running, the HashMatch operator is doing work, but not returning any rows to its parent. This is called a blocking behavior. I don't know how familiar everyone here is with the terms blocking and streaming behavior for operators. A streaming operator is an operator that processes, that reads a row from its child and then as soon as possible returns it to its parent, returns it to its... If you're going to ask a question, please do it in English and not in Hebrew.
No, it's not Hebrew as well. I'll just mute.
Thanks. So a lot of operators are so-called streaming operators, which mean they request one or more rows from their child, and then as soon as their work is done, they return something to their parent, which also causes an execution plan to immediately start producing results. You probably have seen queries where the query does a lot of work, you hit execute, it immediately starts returning rows to the screen, and then still runs for several more minutes before it's finally done. That's because operators are streaming. Blocking operators are different. Blocking operators, and the standard example here is sort. For logical reasons, sort cannot produce any output until it has read its entire input. And blocking operators are the operators where you have a query on your screen, you hit execute and nothing happens for seconds, minutes, hours, depending on how complex the query is. And then suddenly all your data is there. That's blocking behavior. An operator had to do a lot of work before it could return anything. So like I said, in most cases, the build phase doesn't return any output, which means it's a blocking phase, but not a blocking operator, because the probe phase is different. The probe phase is the second phase in most cases. Aggregation, scalar aggregate, and flow distinct are the exceptions here. Those are the 3 logical operations that do not have a probe phase. all other logical operations do. And what this phase does is it reads rows from the second input on the bottom, which is called the probe input. For each row, it looks in the hash table to find matching rows, and then it returns the data joined as needed as it is processed. What exactly is returned and how the logic works depends, because obviously an inner join or a right outer join or a left anti-semi join all have to do slightly different things. But they all do have to find matches first. And then in some cases there's the final case. That's only the case for left outer join, left semi join, left anti-semi join in aggregation. There's the final phase where all or some of the data from the hash table is added to the output as kind of an afterthought. Here's some more data that you also need to get correct results. Before diving into all those operations and checking how the phases work, I do want to point out some important properties. We all obviously, well, I won't say obviously, we all hopefully know that if you look at execution plans, you always have to look at the properties, not just look at the icons and the pretty pictures. Always look at the properties, because that's where all the important data is. And if you look at the properties of a hash match operator, you want to look at the hash keys build property, because this specifies which columns from the build input are the input to the hash function. So these columns determine in which bucket each row goes. And then there's also a hash keys probe. If there is a probe phase, then this will determine which columns from the probe input are hashed to find in which bucket they need to search. The final important property I want to point out is the probe residual. The probe residual is an additional test applied to all the rows in the bucket. So what SQL Server does is it uses the hash keys build to store rows in their buckets. It uses the hash keys probe to identify which bucket to search. But a bucket may contain hash collisions, a different value that happens to have the same hash value and hence is in the same bucket. That should not be returned as a match if you do an inner join. Or you may have a join condition that has equality as part of its condition, where you use the hashing function, but it also has additional rules for a row being a match or not. So yeah, the key value is match, but there's this secondary predicate that also needs to be tested. All those extra tests are included in the probe residual. Now the weird thing, yes?
I have a question. Is the probe residual is like a predicate in an index seek or index scan operator?
Yes, it's a bit of a weird term, but it's actually just a predicate.
Okay.
And the interesting thing about the probe residual is that there are some cases, a few cases, where a probe residual is not needed. And that's what the demo I'm going to show right now is about. So let's switch to the correct database. Now, when I have a query where I join on a big int column, key 1 in these two tables is a big int. And I'm just going to check the execution plan. I'm not going to run this query because the results are not relevant. If I hover the hash match and zoom in, you will see that there is a probe residual here. So SQL Server looks at this query, says, oh, this is a big int. There might be hash collisions. So even if I find rows in the same bucket, I still need to test whether key 1 from the build input and key 1 from the probe input are actually the same value. I have a lot of similar queries here. I'm not going to check them all. But here is another one where I'm joining on not a big int column, but an integer column. And in this case, you will see that there is no probe residual property here. That's because if you use an integer column for your join condition, then SQL Server knows that it has ways to give you a collision-free hash function. A hash function is collision free if it's guaranteed to never have hash collisions. If that's the case, which here it is, then this probe residual is not needed. And SQL Server can just say everything that's in the same bucket is guaranteed to be a match because it cannot be a collision. Now with small int, the same thing happens. There's no probe residual. With tiny int, there's no probe residual. It gets interesting when you start combining things. So in this case, I have a small int and 2 tiny int columns. That's 4 bytes total. And if I do 4 bytes total, and I click the correct button, you will see that there is still no probe residual property. If I go to 5 bytes, an integer and a tiny integer, that's when all of a sudden we do get this probe residual again. So that's apparently the cutoff point for integer values at most 4 bytes. They can be spread out across multiple columns. SQL Server can guarantee that there will be no collisions in the hash table. Above 4 bytes, collisions start to be possible. It gets really interesting when you use incompatible data types. When you use incompatible data types, even though you are within the 4 byte limit, you do get a probe residual. So here I'm matching an integer to a small int. You would say that's 4 bytes, and still there is a probe residual here. The weirdest test I did in this context is I have data2 is a small int column. So this is a small int. I'm explicitly casting a small int as a small int. For the second table, I'm explicitly casting a small int as a small int. So I'm doing a lot of needless stuff here. But SQL Server is quite simplistic. It says, oh, you're casting stuff, you're doing a function, I don't trust you anymore. So I'm going to add this probe residual. And that was the wrong button. It should have been a box. I didn't mean to cross it out. So that's rather weird, but that's just SQL Server saying, if you're doing functions on it, I'm getting a bit more distrustful. I'm not going to analyze the function. I'm just going to err on the side of caution. Obviously, when you do a smaller than, that's something that a hash match algorithm cannot possibly do. Hash match algorithm can only be used for equality. So this data2 is less than data2 will always have to be part of the probe residual. But what I discovered as a funny fact is when there is a probe residual, it's always the complete test. So it is the data2 is less than data2, but it's also this test. Even though data1 is an integer, there cannot be hash collisions. This test is still included in the probe residual if a probe residual is needed at all. So the conclusion, normally you will find a probe residual. The only case when the probe residual is not there is if you have equality conditions only on one or more integer columns with a combined size of no more than 4 bytes and with no functions used at all. Every other case you will get the probe residual. Yeah, that's where I needed to be. Questions on that?
I'm trying to think if we have any actionable thing to take from this.
Probably not.
An optimization we can make to queries.
And now I personally don't even know why the probe residual isn't just there every time. Comparing two integers is such a small operation. It's just 1 or 2 microprocessor operations. So I don't even know why Microsoft decided to optimize it out when it's not needed.
Okay.
But I'm just describing all the stuff you may find, and at least now when you run into a hash match and there's no probe residual, you realize, oh, there's not a bug here, that's because of this reason. That's the only actionable thing you get from it.
Okay, thanks.
So let's move into the build phase. When SQL Server runs a hash match, like I said, the first phase is the build phase. And the build phase is rather simple. It simply initializes the build input and gets the first row from the build input. Obviously, if the build input is empty, this is rather boring. So let's not be boring. Let's assume that there is something in the build input. What SQL Server then does is it computes the hash for that for that row. and then add the row to the corresponding bucket. We already saw how that worked because I went over that at the start and I ran a demo for that. And after that, it gets the next row, and it repeats that over and over again until all rows have been processed, and then it closes the input, and that's it. So apart from the complex part of computing a hash and how does a hash table work, this is actually rather storing. Read a row, store it, read a row, store it, continue until done. The end result is, of course, that the entire build input is in memory in the hash table. And I'm a bit surprised that nobody has yet asked, but what happens if your memory overflows? But maybe you all looked at the agenda and realized, oh, that's for next week, so I won't make myself look stupid by asking that question. And now you don't have to anymore because I made myself look stupid by asking that question on your behalf. Anyway, because next week will be about memory overflowing, today we will not look at memory overflow at all. This week, this session, we will live in the happy fairy world where memory grants are always sufficient and we never spill to disk. Yes, this week we're happy. Next week we are sad. So after the build phase is over, the entire build input has been copied into memory in the hash table, spread out across hundreds, thousands, or even tens of thousands of buckets. And each bucket will have just a few rows, ideally. The probe phase is where the differences for each of the logical operations start. So let's start with the inner join. If you look at the probe phase of the inner join, what SQL Server does, of course, it starts by initializing the probe input and grabbing a row. And again, if the probe input is empty, oh, so boring. So let's assume that there is something in the probe input too. SQL Server computes the hash. Now it knows that if there is matching data, it should be in the corresponding bucket. So it searches that bucket. If no match is found, sorry, this row from the bottom input had no matches, move to the next row. Repeat, repeat, repeat. If a match is found, then the joined row will be returned. And whenever an operator returns data, it also returns control. So the hash match in a join combines the two rows, creates a new output row with data from the two tables, and returns it to its parent. But when the parent asks for a next row, it will continue where it was and check the same bucket to see if there are more matches. There is no guarantee that their data is unique in a hash match. There may be multiple copies of the row with different other columns or with the same other columns. So it continues to search the same bucket. And every time it finds a match, it returns the row, returns control, waits until called again, and continues to do that until it has reached the end of the bucket. And at that point, it says, okay, now I'm ready to move to the next row. That's how an inner join works. For a right outer join, SQL Server has to make just a single change. A right outer join means that rows from the second input, the probe input, that have no match should also be returned. Well, that was in this branch, and this is the only change. So if while processing the probe input, we find a row that has no match at all in the bucket, that row is still returned. That's the only change between an inner join and a right outer join. They're very similar. So to sum it up, the build phase is the same for both. And like we saw on the overview, everything is stored into memory. Nothing is returned during the build phase. So this is where the operator blocks. But during the probe phase, the operator streams. You see it constantly return rows, return control, and then move on to the next row. You also noticed that if you follow the logic, the order of rows from the probe input never changes. If the probe input is sorted, then the output will be sorted as well. But I'm going to add a star here. That star is for next week. Because in reality, a hash match operator can run out of memory, this behavior of retaining the order of rows from the probe input is not a guaranteed behavior. And SQL Server will not rely on it. SQL Server loves to rely on, oh, I sorted the data here, and then it goes through several other operators, and then I need it sorted, but it is still sorted. SQL Server loves to do that, but with a hash match, it can't. Even when it could, if we knew in advance that it won't spill, SQL Server knows it can spill, and when it spills, the order changes. But in the demos I run today, you will see that this order is indeed retained. So let's do this demo, and I just check
Can
my
I
time.
ask a question?
Yes.
In the first phase, not the joins, the probe.
Yes.
Can you say a bit? Talk about how the ranges of the buckets are chosen. Like it's probably based on statistics and stuff, right? Because like how the buckets themselves, the ranges of which hash, like for example, how many values are included in each range of the buckets, like how to do load balancing of the number of records that are anticipated to be matched to each bucket, or can you talk about it a bit?
I can talk about it, but it will actually be a very tiny bit, because this is completely...
Very what? Very?
I can talk about it, but it will definitely be a bit. You said talk about it a bit. It will be a very tiny bit. Microsoft has not documented anything about how its hash value functions work, what hash functions it uses. And there are thousands of documented hash functions because it is a very popular research topic. If you think about it, come up with a function to generate a number from 0 to some upper limit and try to minimize the hash collisions, but you don't know anything about the input data. That's a tough task, and that's why there's a lot of research and many people graduated on this, and it's a constantly improving topic. You already saw that when I first built this session and created my demos, I was also running SQL Server 2016. And then when I later did the same session again, and I had switched to SQL Server 2017, my first demo didn't work anymore, which is why I had to figure out new ranges and why I now have 2 command blocks. And I now have SQL Server 2019 on my machine, but I just keep running this on SQL Server 2017 because I'm too lazy to go through the routine of finding yet another set of hash collisions. But between 2016 and 2017, the hash function apparently changed, which is why on 2016 and 2017, that first demo where I showed the hash table produces different results.
So, but if I'm talking like from above, not about like diving into the mathematics of it or something. If, for example, I have the tables that are participating in the match, in the hash match, they are unique. Okay, like if the key of the join is unique, and there is one value per one record per value. I'm just saying, for example, and let's say that they are not unique, and there are many values, same values of the join condition of the join column per record. The same value is in many records. The buckets will be still the same.
Frankly, I don't know. That's because Microsoft has not documented anything about this. I know that there is logic in the optimizer to figure out which hash function to use, how many hash buckets to use, and that's all I know. It's completely undocumented, and we have no information about this.
No, but
so
I'm
there
pretty
is no
sure
like
I'm
recommended
just
steps or manipulation that can help, because we know that if, for example, the join is between one table that is unique and another that has a lot of ranges, so it's maybe works better, faster. Maybe we should strive to have unique and then join. Like there is no manipulation or best practices to do to make the match happen better.
What the optimizer does try to do is switch the order of tables if needed to ensure that the table that is estimated to be the smallest will be the build input. And it has nothing to do with optimizing the hash buckets, but optimizing memory usage. If one
just
table
by size,
is,
not because of the different values it has.
yes,
It's
you often see
by
hash
size.
match joins in data warehouse queries where you, for instance, have a dimension table with 100,000 customers and a fact table with 10 billion sales. Guess which one you want to have stored completely in memory? That will be the 100,000 customers and not the 10 billion sales.
Although the 10 billion sales might belong to only a fraction of the customers, and then the different values will be smaller than the ones of the older customers, right?
The problem is if those 10 billion sales belong to only a few customers, you know that after the hash match, but you start by stuffing everything in memory. And when you process the build table, so you can try to trick or force the optimizer into doing it wrong, but in this case, you would definitely be shooting yourself in the foot.
So it stores the entire table. It doesn't take, like, let's say that on the bigger table, the fact one, it has a clustered index or non-clustered index on that column. It will not take only the index itself and do the hashing. It will take the entire table.
No, it will, it will store the rows it needs. So if we jump into a demo, I was going to do this demo anyway. But I'm going to show you now that the build input, I don't care what columns are in the table. What I care about is the output list. So it returns a key 1 and a key 2. And I happen to know that I also had a varchar long column in the input that I use for some demos, but here it isn't used. So this is completely unrelated to what indexes there are. And I'm actually showing the incorrect operator. I should have used this one, but in this case, that's the same. So it stores these 2 columns for all the rows returned. And the columns returned there is based on what the query needs.
It's copying the relevant columns it needs and doing all of the
not really copying them. They are stored somewhere, either in the buffer pool or in the somewhere else in working memory. And the hash table just stores a pointer to that memory area and reserves the memory. Make sure it doesn't get freed up again. So it uses all that memory, but it doesn't actually copy it. It just says, okay, this memory should be protected now, and here's a pointer to it.
So because of that, if we are talking about the table of all of the customers versus the table of the fact of the usage of all of customers, and the fact has records only for, let's say, 10% of the customers, and we want to take from the fact table three columns. So it will store, if we will force it to take the bigger one, it will actually take for all the millions of fact records, it will take all of the 3 columns for all of the records.
It will use the columns it needs for the query, for the rest of the execution plan.
Okay.
And the optimizer will always try to put the smallest table on top to minimize the chance of running out of memory and to minimize the memory needed, which is, of course, a very scarce resource on a server with lots of users.
Because like the players here are the records themselves, and each record is unique, even if the key of it is the same as the second record. But the record itself has a pointer to itself. It's a specific record, so it will take all the records. It doesn't matter if the key is the matching column is the same value. It's a different record, so therefore, if it's 500 million of records, it's still 500 million of different pointers. And it doesn't matter that the column has the same value for all the 500 million.
No, because those rows are still needed. If there are duplicates in the build input and duplicates in the probe input, you still expect the Cartesian product of those rows in the output.
Yeah. So it's unique no matter what. It's different records, different pointers to different records. So okay, now I understand. Thanks.
In the interest of time, I need to move on now anyway. So what I have here is a simple demo where I again use a trick to say I'm going to get an ordered build input and an ordered probe input using the same trick as before. Now I'm joining on a combination of key 1 and key 2, so the hash table will be different from the previous demo. And what I want to show here is that the probe input order is retained. Now you could say, how do you know it's a probe input and not the build input? Because they're the same, and you would be correct. So let's move to the right outer join, and then it gets more visual. Because here I do the same trick, but with a right join. And now you will see that the probe columns are on the right. As you see here, the probe inputs, the probe columns are on the right, and this is actually completely sorted, while the build columns are not sorted. There are some weird nulls in between because we have a right join. So this row that doesn't match is indeed returned as soon as it's read and not at another time. So we see here in this simple demo confirmed what I said, and let's move back this flow chart, that every probe row is read and then either immediately returned with the join results or returned on its own, and then the next row is read. For a left outer join, basically the left outer join is similar to the right outer join, but now we need to have a way to find which rows in the hash table were not matched. And that needs a bit more work. So what SQL Server does for a left outer join is the same flow chart as an inner join, with one addition, and that's this. When a row is, when a match is found, then the row in the hash bucket is marked, saying, oh, I have at least one match for this row. And it does that for all the matches. Then later probe rows might have a match on the same row, and it's marked again. Well, it's yes or no. Marking it yes multiple times doesn't hurt. But why is this mark done? Because after the probe phase is over, there will be a final phase where the entire hash table is read and all the unmarked rows are returned. This is actually the trick I used in the first demo to get insight into the data in the hash table. By having an empty probe in the first demo, I guaranteed that probe get next, no data, close, and everything in the hash table was still unmarked because there was nothing in the probe. If there is actual data in the probe, then this will return just a part of the hash table, only the rows that haven't been matched yet. A full outer join is basically the combination of a left and a right outer join. So you see the same changes as you see for a left outer join and the same change as you see for a right outer join.
Where does this mark happen? Does it mean we have another extra bit or byte in each bucket?
Yes, it's a bit in the bucket, and I'm not even sure if it doesn't do that for all the phases. The fact that the mark is not needed for an inner join doesn't mean that Microsoft at one point had to make a decision: are we always going to flip this bit, or are we going to make it conditional? I don't know what they chose. For that, you would actually have to use a debugger and look in the internals, and that's something I refuse to do. I don't want to get into debuggers. I love internals, but not at the debugger level. So if I now look at the left outer join and execute this query, you will see that again, you will see that at the start is only the same data we had at the inner join. So the start looks like we are just doing an inner join. And then near the end, when I keep scrolling, suddenly only the rows are returned in sort of a semi-random order that are not matched. The letters F and B are not matched because of how I filled the tables. And these are now returned in a weird semi-random order. I'm saying semi-random, not random, because no matter how often I run this, the order will always be the same. This is the order of the hash table, as I used in the first demo already. But now we see it in a real left join where there's actual matches that are all processed at the start, and the non-matching rows are returned at the end. I'm going to skip the demo for the full outer join because it's basically the same thing. But I do encourage you to go through all the demo code later and run it for yourself, because I have to skip a lot of demos in the interest of time, and I want you to be able to run them anyway. So a left semi-join. A left semi-join is a weird type of join. You cannot use it in your query directly. If you type left semi-join, you will get a wiggly and an error if you still try to execute it. But the left semi-join is something the optimizer can produce, And it's sort of the equivalent of a where exists. A semi-join means I have a row in the left data, or the top data in this case, and I want to know if there is a match in the right data. And if there is a match, or even multiple, I don't care how many, then I want to return the row. And if there is no match, I don't want to return it. So actually the same logic as a where exists. And if you use a where exists in your query, you will very often see a left semi-join in the execution plan. And the left semi-join actually runs very similar to the left inner join. The only difference is that the matching rows are not returned. So what SQL Server does is it reads the probe input, it searches the bucket, and it marks the rows in the bucket, so in the top input in the hash table, that have a match, and it marks them all without returning anything. And it does this for the entire probe input. Then at the end, it goes to the hash table and it returns all the marked rows, all the rows that have been matched during this process. And then there's also an operator called the left anti-semi-join, which does the exact same thing, except that it returns the unmarked rows. So this is the not exists. In this case, there is a theoretical other possibility. And actually, when I first started thinking about this session and building my flowcharts, I had a flowchart wrong for the left semi-join because I had expected Microsoft to have implemented a different algorithm. So what Microsoft could have done is to return rows here if they are not marked yet. The reason they are not returned here now is because if there are multiple rows in the probe that have the same key value, you don't want to return them multiple times. We don't care about marking them multiple times. Of course, we could use that mark here to only return the rows once and then not return anything here. But apparently Microsoft chose to use it like this. That was probably simpler. I'm going to skip this demo, but if you run the demo, you will see that both for the left semi-join and the left anti-semi-join, you get your data completely in semi-random order and not streaming at all. For the right semi-join, the right semi-join is the same as the left semi-join, but now we are interested in rows from the second input that are not matched in the first. So here the same logic happens again. When a match is found, we simply return the row from the probe input. We are not interested in what is in the hash table, just that the row is there. When the row is there, we return the probe, done. We are also not looking for more matches. We don't care how often the row matches, we just care that it matches. So this is what a right semi-join does. And a right anti-semi-join, well, big surprise, returns the row if there is no match. And if there is a match, it simply does nothing. Here there were again different possibilities, and this is one where I do want to show a demo quickly because I figured when we're not interested in the duplicates in the build table, why store them at all? Maybe Microsoft has chosen to remove the duplicates while storing the data. And by the way, I'm skipping most of the comments, but I put them in for a reason, because in some of the demos I had to do some weird stuff. Like for instance here, I changed 100 to 101 here, just to get the data in the correct the execution plan I wanted. I have comments everywhere about how I had to fight the optimizer sometimes to get the execution plan I wanted. But what I want to show here is I wanted to look at how can we figure out whether SQL Server stores the entire build input, or whether SQL Server says, I don't care about duplicates in the build input, I'm never going to read them, so I'm going to filter them out while building the hash table and save some memory. So what I did is I used a slightly bigger set, and this is a right join. So here I know that everything in the build table is needed. And if everything in the build table is needed, then we get a memory grant of 1,888 kilobytes. And the memory usage here is 776 kilobytes. Let's keep that number in mind. Now we have the same query, But now we do write anti-semi-join. In this case, the duplicates are not needed. So SQL Server might be smart enough to say, I'm not going to store them, which means I need less memory. Well, SQL Server might be, but it's still a memory grant of 1888. And the memory grant info still says that the same 776 is used. So this already gives me a suggestion that SQL Server does not remove the duplicates while building the hash table. It could have, the logic can be built, it's possible to specify it, but Microsoft chose not to. Even more interesting, if I make the set even larger, here the set is so large that Microsoft says, oh, I want to remove those duplicates. I know I don't care about those duplicates. I don't want to fill the memory with duplicates I don't need. I want a smaller hash table. But because the hash match write anti-semi-join cannot do that, I'm going to aggregate the data first. And this is where all the duplicates are removed. And now we actually save memory. But SQL Server needs an extra step for that. So this definitely proves that a write anti-semi-join does not remove the duplicates. It's a choice Microsoft made while building the operator. They could have chosen differently, that had benefits and downsides, and this is their choice. Now, one weird operator that hashmatch also can do is union. Not union all, but union. And union does what the union T-SQL keyword does. You have two sets, you combine them, but all the duplicates should be removed. And duplicates, there are three types of duplicates that union cares about. The duplicates in the top input, so the top input has duplicated rows, they need to be removed. The second input can have duplicated rows, they need to be removed. And then there can be rows that are in both the top and the bottom input, and they also need to be returned only once. That's a huge difference with concatenation, where they would all be removed. Concatenation is the same as union all. For a union, what Microsoft chose is we're going to run the same build phase as always. Just store the entire first input in a hash table. Then while processing the probe input, if a probe row matches something in the hash table, then we're not going to return it. That is a case of a row that would be in both inputs. It needs to be returned only once, and to ensure that, SQL Server does not return it when it finds it in a probe row input. When a row from the probe input is not matched, then it will be returned. Now the probe input is completely unsorted. This means that if you look at this, there is nothing to remove duplicates from the probe input. I could get a row that's completely the same as a row I had 5,000 rows ago, and it will be returned. A hash match union can only be used if the probe input is already guaranteed to be free of duplicates, because the hash match cannot provide that guarantee. What the hash match can do is provide the guarantee that something that is in both inputs is not returned twice, and it can also provide a guarantee that something that is duplicated in the build input is not returned twice, because while returning rows from the hash table, it will remove the duplicates. And here again, SQL Server could have chosen to remove the duplicates while building the hash table, and they chose not to. And I used a similar demo, similar queries as before to prove this. I'm not going to show those demos, but here we see that the hash match union is again blocking in the build phase, streaming in the probe phase, keeping the order of the probe input the same, but only returning rows that are unique to the probe input. And in the final phase, it returns rows that are only in the build input and rows that are in both inputs, while removing the duplicates. There are many other ways this could have been done within a hash match. None of them are used. This is how it's actually working. The demos that I'm not going to run will show that if you look just at the order of the rows, you get your indications that this is how it works. Oh, I'm running way over time. Anyway, I wanted to talk about a few more logical operations, and aggregate is the first that has a different build phase. So the aggregate is the first logical operation that actually does something different while building the hash table. So we return to the build input. the first input. We initialize it, we get the first row, we compute the hash, and now instead of simply saying, oh, we can add it to the bucket, no, during the build input, we search the bucket to see if the row for those key values already exists. If that row exists, SQL Server will update the aggregates in that bucket. If the row doesn't exist, it will create a row in that bucket and then update it. So in the bucket, you will not store everything in the build input. In the bucket, you will store the key columns, the group, perhaps I should say the group by columns, and the placeholders for aggregates so far. So if we want to have a count star, then when we create the row, the count will be 0, and when we update the row, it will be increased by 1. If we want to know the sum of a column, then it will be initialized at 0, and it will be increased by the current value from the current row every time we update the aggregates. If we want a maximum and the minimum, we constantly compare the current value to the maximum or minimum so far and update when needed. So at every point in time, if you just interrupt the build phase, you will see that in the hash table, you have the group by columns and the aggregates for all the rows processed so far. And when the build phase is completed, that means that the hash table holds the results we need. One row for each group by value or combination of values with the key and the aggregates. Which also means that we don't need a probe phase. We have the final data in the build table, and the only thing we still need to do is a final phase where we return all the data from the hash table. And that's it. So a hash match is also blocking in the build phase and stores intermediate aggregated data. There is no probe phase, which makes sense because a hash match aggregate only has one input. It doesn't have a probe input, so it can't have a probe phase. And then in the final phase, all output is produced in whatever weird order the hash table happens to have in memory. Let's see if I'm going to run this demo or not. No, not interesting at all. You'll just see that if you group by key 1 or group by key 2, the amount of data that we process is the same. But SQL Server has statistics where it knows that key 1 and key 2 have different number of unique values. And so the hash table will be larger or smaller, and the memory grants will be larger or smaller, depending on which value we aggregate by. So the optimizer knows that in this case, not all input is stored in the hash table, but only the output is stored in the hash table. And the last normal operation is the flow distinct. And the flow distinct is the weirdest of all. Again, we look at the build phase, not at the probe phase, because there is no probe phase. It has only a single input. We start by computing the hash. We start by searching the bucket, just the same as for aggregation. But now, if we find a match, if we find no match, we create a row in the bucket, and we immediately return the row and return control until we're called again. And then we keep doing that. And if we ever find a match, then we just ignore that row. Why do we ignore that row? Because we're interested in distinct values. And if we're interested in distinct values and the row exists, then we have already returned that row. And we don't want to return it again. So this basically does the same as aggregation, but without having aggregates, and a very different behavior pattern. This is the weirdest one because it's the only hash match that streams during the build phase and not during any other phase. It also retains its order of rows from the build input, but again, only if we don't run out of memory. Now, the sad thing about flow distinct is that it's more expensive than aggregate, and aggregate can do the same thing. So you will hardly ever see a flow distinct, unless you have some interesting demos. To skip some stuff, but here, for instance, if I look at these two queries and just look at the execution plan, you will see that the first query uses a flow distinct and the second uses aggregate. Both only want distinct data, but aggregation can do that. Aggregation returns one row per key one value. So this query uses a flow distinct, and this one uses aggregate. Now, if I run this query, and you have to, it's fast, so you have to watch the screen carefully. I'm going to do it a few times, but you will see when I click execute, rows start being returned immediately. Whenever I click, it immediately starts returning rows and continues to return rows. This is the non-blocking, the streaming behavior. The second query, where I have a hash match aggregate, you can actually see, and I'm going to click it now, that there is a short delay before rows are returned, and then all the rows are there. Well, returning the rows still takes some time because it's a lot of data, but that's mostly client processing now. So there you see the difference, and if the data is actually a lot larger, then that delay can become a problem. So why does SQL Server sometimes choose hash match aggregate and sometimes hash match flow distinct? Well, let's first remove this and look at the execution plan. You will see that it will aggregate. You will see that the input is a lot of rows, and the output is estimated to be 3,540.41 rows. And now look here, this is below the expected output, this is above it. So if I now look at both execution plans, here SQL Server expects to have to process the entire input, 495,786 rows. And here it expects to have slightly less logical reads. And that's the benefit of flow distinct. Hash match aggregate always reads the entire input before it starts returning rows. And top can only stop calling it when it gets rows. Flow distinct returns rows immediately, so top can start calling it. And that becomes more visible if I use a much lower top value here. Because now SQL Server will say, okay, top will only ask for 3 rows, so hash match will return 3 rows. And based on the statistics, I expect to have to read only 281 rows to get the first 3 unique values. And that's a huge saving as compared to processing the entire table. So that's why flow distinct is sometimes used. I know I'm officially out of time. Can I still continue?
Yeah, how much time do you need more?
I think 5, maybe 10 minutes tops.
Yeah, sure.
Thanks. So these are the 11 operations that everyone agrees exist. But as my son already explained in the intro, there are 11, 12, or 13 operations depending on how you look at it. So let's look at hash match scalar aggregate, the logical operation that exists but doesn't. It doesn't because you will never see it in an execution plan. Hash match scalar aggregate is simply called hash match aggregate when you see it in an execution plan. So it appears to be just the normal hash match aggregation. You never see that it's a different logical operation until you actually look at it, at the details. You will only find a hash match scalar aggregate if you have batch mode execution. It will not run in row mode execution. Hash match scalar aggregate simply returns a single row with the aggregation of the entire set. So if you do a select count star from table, that's when you have a scalar aggregate without a group by. Normally in row mode, that would always use a stream aggregate operator because that's simply faster. But in batch mode, you run into the problem that stream aggregate doesn't support batch mode. In the SQL Server 2012, this actually had the unintended and funny side effect that a query that uses aggregates and group by is faster, much faster than a query that uses aggregates and no group by. And sometimes you even had to rewrite your queries to do weird stuff to get them faster. In SQL Server 2014, Microsoft said, we can't have that anymore. So they decided to build specifically for batch mode a hash match function that does a global aggregation so that we don't have to fall back to row mode. Because we're returning only a single value, the hash table will not even be a real hash table. It's only a single bucket. So it's only a single bucket, or if you have multiple threads, then it's a single bucket per thread. How do you recognize a hash match scalar aggregate? Well, not by looking at its logical operation, because the execution plan labels it an aggregate. But you can look at the properties and you will see that the hash keys build property is empty. There is no hash keys built. And that's how you recognize a scalar aggregate. And then we looked at the logical operation that exists but doesn't. And this is the logical operation that doesn't exist but does. If you understand what I mean. You don't. Probably that's intended. So the hash match partial aggregate is one you will see in an execution plan. But it doesn't do anything special. A hash match partial aggregate is exactly the same as a hash match aggregate. And Microsoft decided to label it a partial aggregate so that you, the user, can see, oh, it's doing a partial aggregation and it's doing something else later, more aggregation. So it can do a real aggregate, it can do a scalar aggregate, and it's doing the exact same thing as when it would have been labeled an aggregate or a scalar aggregate. Well, it wouldn't be labeled scalar aggregate anyway, but a partial aggregate doesn't do anything special. It just does the same thing. So let's jump into the demo. And here I need to make sure that I'm in the correct compatibility level first, or my demos will fail. Here you will see an example of a scalar aggregate. This is a query that uses batch mode execution. It helps to enable the execution plan as well. This is a query that uses batch mode execution. And here you will see a hash match. And this hash match runs in batch mode. But if you look at the properties, you will see that the hash key is built. And let's expand this. And you will see that even expanding doesn't give us anything. The hash keys built is empty. You will also see that the estimated number of rows and the actual number of rows are 1, because there is no group by. On SQL Server 2012, this would have run in row mode and would have been slower. Since SQL Server 2014, the hash match aggregate only in batch mode plans can be used to perform a scalar aggregation. Now we're going to switch to another compatibility mode, because otherwise this execution plan will be optimized in a smarter way. And I was too lazy to come up with a different example. So in this query and in this execution plan, you will see a hash match partial aggregate. This is a normal hash keys aggregate, or in this case even a hash keys scalar aggregate, because in this case there is no hash keys built. So why is it called a partial aggregate? Because it runs in a parallel section of the execution plan. So we want a minimum. What SQL Server does is it processes data across 8 threads on my laptop. On each of those threads, it finds the minimum. Then it gathers the streams, and then in a serial section, it aggregates the 8 remaining rows to find the minimum across those 8 rows. And that's why it's called partial aggregate and aggregate, to help me as the consultant coming in to fix the performance, to understand why there is 2 aggregations for a query that only needs a single aggregation. Because here it does partial aggregation. And that may be important to know, because sometimes in partial aggregation you get different aggregate functions than you would expect. For instance, if you do a count star, then it would do a count star here. But it would sum them here, because if there's 5 rows on thread 1 and 10 rows on thread 2, then you need to sum the 5 and the 10 to get 15 as the total number of rows. Let's reset the compatibility level. And that's where I'm going to ask, are there any questions? Because the rest of the agenda is for next week. So, are there any questions?
All right. Anyone? I have a question. You presented many flowcharts during the session, and as far as I understand, all of the flowcharts talked about row mode execution. What about batch mode execution? Are they all the same? The same behavior?
They're all about row mode execution. Batch mode execution is, well, even those flowcharts are my research, they're not documented. Batch mode execution is even less documented. They will not be exactly the same because they process entire batches as once, and they also have, I know that within batch mode, there are all kind of weird optimizations to benefit as much as possible from caching. For instance, one example I happen to know is CPUs have a thing called the level 1 instruction cache, where a set of code, machine level code, is stored as close to the CPU as possible so that it can access instructions very fast. Now, because that cache is very small in size, all the logic to handle a row is often, all the possible logic to handle every possible row often doesn't fit. And if you standard do your coding, that means that, oh, we need to have this special code, and the level 1 cache has to be reloaded with new instructions. So you have a lot of level 1 cache misses. One of the many things that Microsoft did when developing batch mode was saying, okay, let's recognize that for some rows we need to do stuff that's currently not in the level 1 cache. So instead of constantly swapping data in and out of the level 1 cache, we just set those rows aside for a while, and then process the rest of the rows that we can handle with what is in the level 1 cache. And then we reload a new set of instructions in the level 1 cache, and we handle all the rows we had set aside at first. Adding all that logic to the flowcharts makes them incredibly complex.
Yeah.
Plus, I have no clue how it is actually done, so it would purely be guesswork.
Okay.
So yes, all my flowcharts are for row mode. For row mode, they actually are correct. For batch mode, they, let's say that they show the intent of what is going to happen, but the actual implementation is a lot more complex.
Okay, thanks.
But you can still use the flowcharts to get an idea of roughly what is going to happen.
Yeah.
More questions?
More questions, anyone? I think people are shocked. we are all still trying to get our heads around what just happened here.
Okay, this was only the level 400 part.
Yeah.
Next week we'll get really messy and into the internals. That's the most fun part of this presentation.
Yep, looking forward to that. So everyone, next week is part 2. Next Monday, same place.
One more remark, Guy?
Sure.
I have my email and my Twitter handle on the screen. So if you are indeed busy processing everything and later today you are suddenly like, I should have asked that, send me an email or hit me on Twitter and I'll see if I can answer the questions.
Excellent. Great. So make sure you register for part 2 next week and attend the session.
Yes,
and I think that's it. Thank you very much, Hugo.
You're welcome.
I will see you again next week.
Thank you for having me.
Okay, bye everyone.
Bye everyone. Thanks for watching.
Thanks all.
Thank you very much.